Hello, and welcome to the third video on thermochemistry, which we're going to talk about calorimetry today. And so in the past we've talked about enthalpy, we talked about energy and work and how all of that is related. Today we're going to talk calorimetry. Since we can't know our exact enthalpies of my reactants and the products, because that's not something we can currently measure. We measure our change in enthalpy through a process called calorimetry, which is looking at heat flow. To do this, we use something called a calorimeter, which is where the name calorimetry comes from. And there's a picture of a calorimeter on your left, so you have typically two styrofoam cups or two cups which provide insulation, which prevents heat loss to the outside. You have a reaction taking place in here, a cork stopper or a insulator stopper to not lose heat from the top, a glass stir rod to mix the reaction, and then a thermometer to measure the temperature change of the liquid in here, which is typically water. To do calorimetry, we need to know a couple things. One of them is we got to be familiar with this term heat capacity and specific heat. And these are two different things. They're very close, but they are different. So heat capacity is the amount of energy required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius. Typically we give this for 1 mole of substance, but heat capacity can be any amount of substance that you have. So heat capacity is just energy to raise the temperature of the substance by 1 Kelvin or 1 degree Celsius. So here you see a table that you have substances, and we don't have heat capacity listed. We have what's called specific heat, which we're going to get to on the next slide. Okay, but this is heat capacity is just energy to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius. If we talk specific heat, whether we call it specific heat capacity, as is the first bolded set, or just specific heat, we're looking at the amount of energy required to raise. So again, we're looking at energy, and we're raising the temperature of 1 gram of substance by 1 Kelvin or 1 degree Celsius. If I could draw a straight line, it'd be really nice. But in here, we're changing 1 gram of substance by 1 degree Celsius. For example, if I have exactly 1 gram of water at a temperature of 14.5 degrees Celsius, and I add 4.184 joules of heat, or I add that's 1 calorie, little c calorie, of heat, I can raise that by 1 degree Celsius. So I went from 14.5 to 15.5 because the specific heat of water is 4.184 joules per gram degree Celsius. So for every 4.184 joules of energy I add, I can increase my temperature by 1 degree Celsius or 1 Kelvin because they fluctuate by the same amount. But that is specific heat and heat capacity. So specific heat is the heat transferred divided by mass times temperature change. This is the equation solving for specific heat, and that's a constant. Typically, I always show my students this equation I write as Q, which is heat, equals M times C times delta T, where Q is heat, my pen's not working for me. M is mass, C is specific heat, and T is temperature. But that's the equation that you'll see in textbooks a lot of times. That's the equation that I show my kids. So if you're solving for C, then you divide by M delta T, because we're looking for a temperature change. Because if we carry this out in an aqueous solution, it keeps the pressure of the reaction constant, which works out really good. The heat change for the system in an aqueous solution can be found by measuring just the heat change of the water. Because we know the specific heat of water is 4.184 joules per gram Kelvin or joules per gram degree Celsius, we can calculate delta H for the reaction using this equation. And so this is why we solve for Q. So Q equals MC delta T. And if we solve for heat, that tells us how much energy the water either gained or lost, and that gives us our delta H because we're in a constant pressure. So again, delta H, that's a triangle, equals delta E plus P delta V. And we substitute and mix all this around. That delta E is the same as Q. And if P delta V is, that's a triangle V. P delta V is, if my pressure is constant, that means pressure change is 0. So this disappears and your delta H equals Q. And that's where we get our enthalpy calculation for this. We perform a lot of these in what's called a bomb calorimeter. A bomb calorimeter looks at, we have water on the outside of a substance and we can burn something inside, is what happens. So we have ignition wires up the top. They light a spark. They light this on fire. This burns, it heats up, and which will then heat the water, and we can measure the temperature change over here with our thermometer. So the heat absorbed or released by the water gives us the energy change of the reaction taking place here. And so Q of the reaction is equal to your negative C calories times your change in temperature. And that's what we're looking for, is our change in energy. And we'll do some practice with this. Because our volume is constant, what we're measuring is, we're looking at the internal energy and not specifically delta H. We're not looking specifically at enthalpy, we're looking at just energy. So we're looking at delta E and not delta H. For most reactions, the difference is small enough that we call it negligible. We just refer to it as the same thing. But we are actually looking at delta E and the energy change, not your delta H, your enthalpy overall. Because there is no volume change. But that is where we're going to stop. On the next video, I will give you a practice example of how to solve a bomb calorimetry question, and then we'll continue from there. For now, enjoy the rest of your day, and I will see you next time.